Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 12th lecture where we are discussing now the design and development of floating wave energy converter, which is a sequential lecture on the course Marine Renewable Energy Systems Design, Analysis and Development done by Maritime Engineering Department at IIT Gandhinagar. So in the last lecture we discussed about the float geometry . And we said we are having a central buoy and we will connect 4 bean shaped floats to the central buoy. And we identify various design parameters which will control this for the given wave direction. And we said that these central buoy connects these floats with a hinged connection and the whole design is dependent on how rugged is this connection, and therefore at this point the bean shaped buoy rotates and we induce a virtual rotational damping to the central buoy to compute or to arrive at the harnessed the absorbed power by this. However, when you start using this for a torus system, you cannot have the same design as you see here. So, I will leave this as a small homework to you, that if I have a torus system, a torus buoy, okay, how do I connect it to a central buoy to harness energy? So, I can give you a hint. A central buoy is connected here, and you have to think about certain arrangement by which this torus will be connected to the central buoy. Remember, in the previous case, the energy harvest was done by the rotation of the buoy about the hinged point, whereas in this system design, the torus will also rotate about this axis as well as it will flutter about this axis, is it not? So, one has to think about the connectivity of the central buoy to the torus buoy. So, that is again a question of interesting innovation for you. So, I leave it for you now. So, we will continue with this design now, that we have got, let us say, 4 bean shaped buoys connected to a central buoy, and we now call this as my design configuration, for which I am going to find out the performance of this. Okay. So, one can see in this design the CG of the system is concentrated with the central buoy, that is number 1. The center of gravity of the system is well below the center of buoyancy of the system. Okay. So, one has got to choose the design draft of the circumferential buoy and the central buoy in such a manner that this condition is satisfied. Okay. So, how to achieve this? It is very easy, friends. If you want to manage this design concept to be achieved, then we can manage this by adding or by ballasting the central buoy. Okay, by ballasting the central buoy at the bottom, one can achieve this. That is a very simple hydrostatic design, one can as well use it. Okay. So, friends, furthermore, when I say that the central buoy is connected to the seabed using pre-tensioned cables, where this is my water level, pre-tension cables, then there could be one more design parameter which can control the whole efficiency of the working system. That could be the mooring stiffness. Then the different type of mooring. So these are good challenges to make the design further innovative. So here we have used something called taut mooring system, which says the system is with pre-tensioned tethers. Okay, and we have used an initial stiffness AE by L so that the stress in the mooring line is well within the yield value. Okay, so therefore there is no failure of the tethers because of the linear stiffness failing, right. So one can also see how these parameters can also be changed in this design, like we have tested this as an homework. So this is a homework for you for self learning and self innovative design. The further homework is these parameters. Okay, this can be a homework attempt for you. So try to do this and see how you can learn from this further. Okay, now having said this, let us look at the design parameters what we chose for this boy. Okay, so the design parameters are available. Chandrasekaran and Sricharan, 2012 A, 2012 B, 2012 C. So these are the papers where you can see these design parameters published in refereed journals, but for our understanding I am giving you these parameters at this moment here. So initially a scaled model of the device will be examined. So now the water depth at which this study is done is at 5, 10 and 15 meters. The weight of the central buoy is about 8,300 newtons. The buoyancy of the central buoy is about 11,850 newtons. Let us say the weight of the float. Now the float has got different configuration. So let us pick up one specific float of the curved closed configuration. Let us say the curved closed, let us say this is one configuration we call S1, this is another configuration we call S3, this is another configuration we call this is S2, this is S3, this is another configuration which is S4. This is open, friends, this is open, but this is closed. So for S4 configuration it is approximately 3,220 newtons. Now the design draft of the central buoy, we call this as design draft of the central buoy, is about 1.5 meter. For the floats, let us say for the float S4 is about 0.3 meter. So you remember, friends, the diameter was 0.6 meters, we said 50% of the diameter is the draft. Now the freeboard of the central buoy is about 0.5 meter, is above water, and as far as for the floats are concerned, let us say S4 float is about 0.3 meter. Now the length of the connecting arm, the central buoy connects the float and the connecting arm, this length I am talking about. Okay, this is about 1 meter. Of course, this length is not considered. This is L, which is about 2.4 meters. Am I right? This is already stated in the previous one. So 2.4 meter, we call this as L effective. I call this L effective. So L effective is 2.4 meter, and therefore friends, the central buoy connecting, okay, I will draw a line. Let me put the buoys around this. I am drawing a schematic view, and we said that this distance is approximately 1 meter. Okay. So now the overall diameter, which we call as d prime, could be 1 meter plus central buoy diameter plus 1 meter. It's about 2.6 meters. Okay, that is the circumferential diameter of the whole system now, at which this is operating. Okay. Now let us look at the formulation of this problem in frequency domain. We understand that the floats now rotate about the hinges. Is it not? We already said that. When the wave is acting the force, and this will help us to absorb the energy. Now this complex oscillation will also cause diffraction and radiation effects, is it not, to the medium. Therefore friends, I must now simulate the wave energy converter behavior similar to spring mass damper system. The dynamic system. Okay, I must simulate it this. So therefore friends, each component of the dynamic characteristics like spring, mass and damper will govern the response of the system. We consider two cases. Case 1, where the mass is connected to the spring. Okay. And case 2, where the damper assumes smooth surface interaction between the mass and the surface. So, let us look at the diagnosis of the case number 1. Look at case number 1. In case number 1, when we displace the mass with certain initial velocity, let us say when the mass is under free oscillation, there will be continuous exchange of energy. Okay. So, this energy will be in the form of kinetic and potential energy by conserving the net energy. So, let us neglect the air resistance. Or resistance by the medium also, let us say, and the fluid medium. No damper, okay, no resistance. Therefore, no dissipation. When there is no dissipation, what will happen? The effect is very simple. The effect is no absorption of energy in the system, is it not? It will keep on vibrating. Now, in the second case, damper is present. In the first case, remember friends, damper was absent. So, then when the mass is moved, oscillating, there is a continuous transfer of energy generated, and this will be absorbed by the damper. Therefore, there will be a decrease in response of the system. So, there is a dissipation. It is this energy what we are focusing at. Therefore, friends, in the case of Beck design, it is this energy which is absorbed from the waves. This is absorbed energy, not transferred energy. Okay. So, now when I am able to compute this energy, let us look at an analogy. Let us look at the analogy. The analogy is the mass is considered in each of the floats. Of the floating wave energy converter. Stiffness represents the hydrostatic stiffness in the present condition. Therefore, the difference in weight and buoyancy will amount to this. Difference in weight and buoyancy will contribute to the stiffness. Okay. Now, the volume of water surrounding the mass which is displaced will develop an opposing force. The volume of water surrounding the displaced mass will develop an opposing force. This will cause something called bobbing effect. The buoy. So, this is very important. This effect is called bobbing effect. This will why the mass is going to oscillate about the spring. So, therefore, friends, the presence of viscosity of water a part of it, the presence of viscosity, that is a part of it, will get dissipated to the medium. The damping effect is therefore induced externally. Externally onto the bobbing buoy. Is it not? Because the bobbing buoy will be tried to be stopped by the external energy, and we call this as power takeoff system. The absorbing energy from the harmonic motion of the buoy to the dash part will also dampen the mass block. Therefore, when we import the geometry to the numerical model, okay, one need to carefully understand the following factors: the properties of the body, mass of each body which is participating in the oscillation. So, this becomes a critical phase of transfer of information to the numerical model. In the next critical phase, would be the modeling process. To be very specific, the mesh generation. This will be of course controlled by the program. By the software or the numerical tool what you are using. So, there should be a trade off between the accuracy and time and the storage space requirements. Generally, the meshes used to determine hydrodynamic coefficients will govern this. One example could be a software tool like ANSYS Aqua, which uses boundary element method, in which surface mesh will be generated. Therefore, the number of elements will be less than of the finite element schemes. The advantage is the number of elements in this case will be lesser than a true finite element model. That is the advantage we have here. Once the meshing is done, then we have to fix up. Once meshing is done, one need to fix up the range of frequency and wave direction. I can give a hint here, friends. The range of frequency depends on what is the natural frequency or the dominant frequency of the device. So, you have a device geometry now, one should run a dynamic analysis of these to compute the fundamental frequency of the device. Therefore, you choose the operational range of frequency in such a manner that the device will operate in the close near resonance mode. The device should be investigated in the near resonance mode. So, you have to choose a frequency range in such a manner that this matches with the fundamental frequency of the system. That will give you the possibility of absorbing the maximum power. Okay. So, that is another challenge what we have in this. Now, coming to the response of the floating device. Let us come to the response of the floating device. The response of the floating device to the wave load is of course complex, because this involves mooring line nonlinearities, motion control systems, and of course wave device interaction. Now, we are looking at the primary investigation. Therefore, the governing input parameters are linearized. So, for primary investigation, the governing input parameters are linearized. In the frequency domain. Okay. So, therefore, we can use linear Aries theory where the C is stated as ideal fluid. The wave ideal means what? The wave amplitude is much smaller than the wavelength. If I have a wave, the wave amplitude is much smaller than the wavelength. It's an idealized condition what we take. So, the floating device, like the one what we are discussing, the floating wave energy converter, is assumed to have 6 degrees of freedom. So, the floating wave energy converter has 6 degrees of freedom and we can represent this motion in frequency domain as follows. Let us say minus omega square m x hat omega is the complex value coming from the exciting force plus the radiation value coming from the exciting force plus the hydrodynamic value coming from the waves plus the force coming from PTO plus the force coming from the moving lines, called equation number 1. So, now to be very specific, the m what we discuss here is the total dry mass. I should say mass matrix. We are talking about 6 degrees of freedom. X hat, what we see here, is the complex displacement component vector, which consists of translations and rotations. Translations are surge, sway and heave. Rotations are roll, pitch and yaw. Fe is the linear excitation force vector. Fr is the linear radiation force vector. Fh is a linear hydrostatic force vector. Fpto is the linear force vector which has linear damping. And Fm is a linear moving force vector. So, remember friends, we are using a taut moved connection. One can also have different kinds of connections here. That is a homework which I gave you in this lecture. So, now I have written this equation expressing the response in 6 degrees of freedom of the floating body. Now, remember the floating body is position restrained by the tethers. Therefore, the F matrix represents the forces and the moments. Okay. So, let us go to the summary of this lecture, friends. In the summary of this lecture, we discussed about the detailed frequency domain model of the floating wave energy converter. We understood that the frequency domain model is a linearized approach and we took two cases. Case 1 which has no damping effect, case 2 has damping effect. So, this case is preferred because this is how we can harness or we can address the captured energy using a linearized PTO. So, friends, stay continued. Thanks for your interest in this lectures on the course offered on marine renewable energy systems by Department of Maritime Engineering at IIT Gandhinagar. We are discussing certain design cases which has been successfully deployed and investigated and designed and patented at our place. This will be helpful for you to learn the novelty in the design and the path followed to achieve at this novel design. Of course, these reference papers are available in the website of the SwayamPrabha course. I would address definitely and request all the viewers to go through all the papers in detail to get the research conceptualization of these ideas. And we sincerely appreciate and thank all the researchers who contributed to this domain of research and renewable energy as a part of this course as well. And we also thank sincerely IIT Madras for helping us to share the patent designs what we did as a part of our research conduct at IITM, and which will be continuing to establish this at IIT Gandhinagar under the premises of Maritime Engineering Department at IIT Gandhinagar. Thank you very much. Stay connected.